Hi folks, my name is Peter Anderson. I'm a research scientist at Google, and this talk is about massive data sets for language guided navigation agents and where to find them. Recently, we've seen a redefinition of what's possible for state of the art vision and language models. And I'm talking in particular about models such as DALL-E and CLIP from OpenAI and the Align model from Google. And what's particularly amazing about these models is that they're proficient at multiple tasks. They have zero shot capabilities. So, for example, a model such as CLIP can achieve very good results for classifying images from ImageNet without using any of the ImageNet training data. And these models are also surprisingly compositional in the way they are able to combine fine grained concepts. So if we look, for example, at an image retrieval task using text and image embeddings from the Align model, we can see that the model clearly distinguishes between very fine-grained concepts such as a Van Gogh Starry Night details versus a Van Gogh Starry Night in black and white or on a canvas or in a dark wood frame, which is very impressive. If we look further at compositionality, here we're doing an image retrieval task using a combination of an image embedding with a text embedding added or subtracted. If we look at the example in the second row, the image embedding of a butterfly on a purple flower, if we subtract the text embedding for flower, we can retrieve an image of just a butterfly, or we can change the color of the retrieved image by subtracting the text embedding for orange. And we can even add the text embedding for rose and retrieve an image of a butterfly sitting on a rose. So this is really quite remarkable. And the reason for these advances is not so much new modeling techniques as simply using much larger models and much more training data. How much training data? So for the Align model, it's trained on noisy web images, image and text data. So you can see from these examples here, the text data is actually, really quite noisy, but the training data consists of 1.8 billion image text pairs for the English only version of this model. And so the power of these models really comes from the huge amounts of data that are used to train them. And so you might well ask, why am I talking about this in an embodied AI workshop? And the reason is, well, first of all, my particular interest is in language guided embodied agents. And so, one problem that we work on quite a bit is language guided navigation agents or vision and language navigation, which is this sort of task that you see demonstrated here. We want to provide a natural language instruction, such as exit the bathroom, turn left, and exit the room using the door on the left, wait there. And what we want is to be able to train an agent that can follow these grounded natural language navigation instructions in a photorealistic and previously unseen environment. And the observation that I want to make is that the training data for tasks such as this is really very limited. And if we just had billions of instruction trajectory training examples, I think it's very likely this task would be much easier. And although this observation is quite flippant, on the other hand, it's actually quite serious because many of the limitations of the current models, such as overfitting to the training environments and poor generalization to unseen environments, a lot of these problems would likely just evaporate with more training data. And so the question is, well, should we not, consider, is there a way that we can stop mucking around with data sets with thousands and tens of thousands of examples and look for hundreds of thousands or even millions of training examples, and how would we possibly do this? And this is the research program I'd like to talk about today, guided by this question. How can we use the available resources we have to generate massive data sets for training language guided navigation agents? So my argument is that there's four parts to this research program. First of all, we need to generate more environments. And one possible way of achieving this is by converting static images and videos of places, which are available at huge scale, into interactive training environments that would allow an agent to somehow move within the image or the video in order to learn navigation. Secondly, if we create these hundreds of thousands of new environments, we would need to annotate them with training tasks, which means generating high quality navigation instructions from a model. Thirdly, using model generated instructions, we naturally need to figure out a way to evaluate those instructions for quality to ensure the quality of the training data. And finally, even though we want to generate these environments and generate these instructions, we obviously still need to collect quite a lot of high quality human annotated navigation instructions to sort of bootstrap this system, to train the instruction generator and to evaluate the navigation agents that we train. And so this is a research program to look at ways that we can scale the training data for language guided navigation agents far, far in advance of what's available currently. And today I'm going to talk in particular about these three aspects of the problem, beginning with the problem of generating environments. So first of all, what's the kind of current situation? So typically for training embodied language agents, there are different simulators and different data sets, but they're typically based on underlying environments from data sets such as Matterport 3D. And there are some others such as Gibson as well, but generally they're at a similar scale. And Matterport 3D contains 90 environments, each reconstructed with a Matterport camera. And as a consequence, I guess, of the relatively small number of environments, what we see when training vision and language navigation agents is that there's a lot of overfitting, that performance of these agents might be quite good in the training environments, but it drops significantly in unseen environments. And so the concept I would like to investigate right now is whether we could take images and videos of places that are readily available at massive scale. Even looking at internet videos, there are hundreds of thousands of real estate walkthrough videos on the internet. And my question is, can we take these static images and fixed videos and somehow make them interactive and convert them into interactive training environments where an agent could learn to navigate? And so what does this look like in practice? Let's walk through it using this example on the right-hand side. Suppose I had, as an example, just a single image as an input, which is image 1 at the top left. And now I'm training an agent that wants to move in such a way as to follow the yellow arrow, which is moving to position 2, shown in the floor plan view at the top right, which is only indicative and not used by the model. What we'd like to do is generate the image in the second row, the prediction of what the view would look like from that new position. And so on, if the agent moves again, following the yellow arrow to position 3, what we would like to do is generate a prediction of what it would look like from that position. And then what we've effectively done is made this image interactive. And so we have actually proposed a model that can do this. The predictions in position 2 and 3 are the outputs of that model. And you can see how they compare to the actual ground truth on the right-hand side. One fairly interesting aspect here is that in the ground truth, in this real environment, the ceiling of this kitchen is actually painted with a fresco of clouds. Now, a model has never seen that. This is an unseen environment, and so the model does not predict that. But nevertheless, it comes up with a fairly plausible prediction of what it would look like to follow those arrows and to move and see inside the kitchen area. So that's the proposal that we're making, to take static images and potentially videos and convert them into interactive environments. And so what we're really proposing is actually a world model for indoor navigation. So typically world models or model-based RL has previously been explored in the context of game environments such as Doom and Atari games. Here, as I'll show with a video, here we're taking this same concept and applying it to indoor environments. So here's a video showing some of the outputs of our model, which we call PathDreamer. Each of these outputs is generated from observations at a single point, and then by allowing or providing some trajectory to the PathDreamer model, and the PathDreamer model then generates observations along that trajectory. So here's a new example. This is the starting image, and these are the predictions from the model as we move in different directions around this building, including around the corner. So we tackle this sort of room reveal problem of what things might look like if we go around the corner. And certainly you can see the model does a fairly nice job of generating consistent and plausible outputs of what this might look like from different parts of this building. One thing you can see, and we're sort of deliberately showing, how far you push this model before it starts to break down. And in general, it takes around 4 or 5 meters before the model starts to break down in its predictions. So one comment I want to make as well is that we've motivated this world model, this PathDreamer model, using the idea of data augmentation, turning static images into interactive environments and using them for training. But world models can be used for many other purposes as well, not least of all is sampling-based planning. So, for example, an agent equipped with a world model can reason about the consequences of its future actions before it takes them and use this to come up with better plans. So let's dive in and have a little look at the details of this model. It's based on 2 stages. The first stage is a structure generator that deals with the segmentation and depth components. And so the model actually takes in segmentation images and depth images as an input. Now, these could be predictions from another model, but in this case, in what I'll show you today, we're using ground truth depth and segmentation inputs. And we then represent these depth and segmentation images as a 3D point cloud, which is reprojected into a guidance image based on the motion of the trajectory. From there, an encoder-decoder stack is used to infill the guidance images, and we also condition on random noise vectors in order to try to capture some of the variability in areas of the image that are completely unseen, for example, when the model looks around corners. The second stage of the model is the image generator. Again, we use a point cloud representation reprojected to a guidance image and a stack of multi-spade blocks in order to generate the hopefully photorealistic RGB predictions of the model. So let's have a look at another example of how this works. If we're given these 3 images from a single observation point as input, so we have the depth image, the segmentation image, and the RGB image. And by the way, all of this data is 360-degree images in equirectangular format. We can then do a rollout of predictions along some planned trajectory, 1 step, 2 steps, 3 steps, and so on. And you can compare the RGB predictions of the model in row 3 to the ground truth of the actual environment, which is previously unseen in the bottom row. And in general, the predictions from the PathDreamer model are quite plausible. One area where I can highlight a mistake is in terms of the ceiling rafters, where the model does not actually realize that a rafter must go all the way across the ceiling in order to actually carry any load. So that was an example of a rollout. I want to show some examples as well of the kind of plausible alternatives that the model can produce by sampling different noise vectors. So on the left-hand side here, we see the guidance images that are the reprojected point clouds used as input to the model. What's important here is the black regions. These are areas where the Path-Trima world model has not seen any part of this environment. It has no information about what could be there. And so these are the areas where sampling different noise vectors will produce different results. And so you can see the Path-Trima predictions on the far right-hand side. For a particular noise vector, it's predicting a window, a chair, and a table. If we sample a different noise vector, it can predict a bed with a cushion and a chair, or a different type of table without a window. So you can see there on the right-hand side, these kind of different plausible outcomes that can be produced. Finally, I want to just briefly introduce a small experiment we've done for using the Path-Trima world model as part of a sampling-based planning approach in the context of vision and language navigation. So what we do here is we roll out using the VLN agent to kind of plan ahead out between 1, 2, or 3 steps into the future by either interacting with the Path-Trima model or the ground truth, which is the actual environment, effectively looking ahead, or a baseline, which represents represents using the information from the navigation graph, but without any visual properties. And so what we can see in these results here is that the green baseline improves performance with forward planning over 2 or 3 steps because it can use some information about the structure of the navigation graph, about the structure of the navigation possibilities that are there. The Path-Trima model does significantly better, though, by providing plausible visual observations that might be seen in the future. And the Path-Trima model closes about half the gap to the ground truth in this example. Right, so I've talked about how we might use the Path-Trima model to generate environments from images and videos. I won't be talking about generating instructions today, but I do want to discuss our work on evaluating instructions. So to put this in context, when we talk about an instruction following agent, we're talking about a mapping, a model that maps from instructions through to some trajectory in a photorealistic environment. An instruction generator performs the inverse operation. It takes some trajectory represented with visual and possibly geometric representations and converts that to a grounded instruction that hopefully a person could follow. Now, while evaluating an instruction following agent is at least conceptually quite straightforward, we just compare the agent's path to the reference path. Evaluating an instruction generator is more difficult. In theory, we can compare the generated instruction to some reference instruction, but what's not clear at all is what metric we should use for that. And so in this work, this is the question we investigate, is how to evaluate model-generated navigation instructions. So our first step is to assemble a large pool of navigation instructions of varying quality and styles. So we begin with human instructions, and we also perturb those human instructions in various ways by swapping directions, such as left and right, by swapping entities, such as in this example, replacing kitchen area with door and door with kitchen area. And we also swap phrases by reordering them in the instructions. This creates a variation in the quality of the navigation instructions. To this group, we add navigation instructions generated from 2 existing models, the speaker follower model and the environmental dropout model. And finally, for even more variation, we add template-based instructions, which we call crafty, to this pool. And here you can see an example of a crafty instruction. These are based on the ground truth object annotations in the Matterport dataset. And so these should be factually correct, but they're quite long, which can make them difficult for people to follow. So the next step, given this large pool of different navigation instructions, each describing the same paths in the Matterport environments and based on the paths from the room to room data set, we now perform human evaluations. To do so, we use Pangea, which is a panoramic graph environment annotation toolkit that we recently open sourced, and we collect 3 human evals per instruction. So for example, here you can see the interface that the human wayfinders are using as they attempt to follow these instructions. They're able to kind of look and move around in these environments, attempting to follow the instruction at the bottom of the screen, which in this case is leave the room and turn left. With the wooden door behind you, keep walking straight. Stop after you go down a few stairs. You can just see the few stairs in view now. So using this, we will basically evaluate the quality of the instruction based on how well our human wayfinders were able to follow it. And we measure that using navigation error, the difference between the goal reached by the navigator and the actual goal location, and also success rate, what percentage of times that navigation error is less than 3 meters, and so on. And so here are the results. And what's interesting is, first of all, to look at the performance of the existing instruction generators from previous work, the speaker follower model and the environmental dropout model. And it's interesting because the quality of the instructions that these models are generating is actually only slightly better than Crafty, the template-based approach, although it must be said that Crafty has the benefit of using the ground truth object annotations. The existing instruction generators are much worse than even the adversarially perturbed human instructions, and far worse than the gold standard human instructions. And the reason this is quite interesting is that these existing instruction generators have already been used very, very successfully for data augmentation, typically improving the performance of instruction following agents by around 5%. And so that's somewhat surprising, given that it turns out that compared to human, the quality of these instructions is quite poor. And so that does suggest there's substantial headroom here to improve not only the instruction generators, but also the quality of the VLN instruction following agents when these generators are used for data augmentation. Now, the primary question of interest here is what evaluation metric we should use for generated instructions, for navigation instructions. And so now that we've established a large pool of navigation instructions of varying quality, and we have human evaluations, our aim is to identify which evaluation metric out of the automated metrics will closely correlate to human performance. And so these are the automated metrics that we look at. We consider textual comparison metrics such as Blue, Cider, Meteor, Rouge, and Spice. All of these metrics require some reference instructions for comparison. We also consider a model-based approach based on BERT score. Thirdly, we consider using vision and language navigation agents as instruction followers and consider evaluations that are based on the instruction following success of these computational agents. The advantage of this approach is that no reference instructions are needed, only the reference path. And finally, we consider a compatibility model, which we propose in this work. And the compatibility model is effectively a dual encoder. It encodes in the one stack a visual and geometric representation of the trajectory, and in the other stack the textual instruction. And it's trained with contrastive loss and large batch sizes to learn to associate which trajectories and which instructions are matched. And so this can then give us a score, which we consider as an alternative evaluation metric. So let's look at which of these metrics correlate with human wayfinding performance. And there's two ways of looking at this. Firstly, we consider a system level evaluation. So this is for when we're wanting to evaluate an instruction generating model. And so we aggregate the scores for each model. And as it turns out, the only one of these scores that has the desired correlation with human evaluations is the SPICE metric, which is negatively correlated with navigation error and positively correlated with success rate and other quality measures such as SPL. And quality here refers to the quality of the instructions as assessed by the annotators on a 5-point scale. So this is a surprising finding because it turns out that blue score, which is typically considered for many text generation tasks, turns out to have no value here whatsoever. And so for evaluating instruction generation models, i.e. system level evaluation, the SPICE metric should be used. Now, the other question is, what about at the instruction level? What if we want to evaluate the quality of an individual instruction as opposed to a model? And in this case, we don't have the ability to aggregate our scores over many, many different instructions. And so the variance of the evaluation metric is much more important. And so it turns out that in this case, the best approach is to use a compatibility model, like the dual encoder that we proposed earlier. And almost as good as this would be to actually use a language guided follower agent. And it turns out that actually at the individual instruction level, SPICE is not effective, and neither are any of the other textual evaluation metrics. And there's also an additional advantage of using computational models and navigation agents for scoring these instructions, and that's the advantage that they don't require reference captions. So overall, I think there's a bit of a warning here for the creation of new tasks. Very often we see new multimodal language generation tasks are being proposed, and automatically blue score is considered as the evaluation metric. And the results here, which show that in this particular case, blue score has no value whatsoever, suggest that we probably should be deeply suspicious of any new tasks that are evaluated with blue score unless a human evaluation has been done that shows that blue score actually correlates with the scores from human evaluation. So having talked about our work on evaluating grounded navigation instructions with some firm conclusions, I now want to talk about the final aspect of this program, which is dataset collection. So recently we collected a new dataset, which we call Room Across Room, or RXR. And this is effectively what the data collection interface looks like. On the left-hand side is the view that the annotator has. They're able to move around and control where they move as they're following a navigation path that's marked with arrows and spheres in the environment, which you'll see. As the annotator moves around, they record with their voice a description of the path that should be taken. I'll show you at the bottom the transcribed text as that description is described. And on the right-hand side, you can see out of the full 360-degree view which parts of the environment the annotator actually looks at, which we also capture. So let me play this annotation example now.
Now you're standing in front of a closed door. Turn to your left. You can see two wooden steps. Climb the steps and walk forward by crossing a wall paint which is to your right side. You can see an open door to your left side. Enter into it. This is a gym room. Move forward and walk till the end of the room. You can see a grey colored ball to the corner of the room. Stand there. That's your endpoint.
So that's the interface that we use to collect a large-scale data set. And so you might wonder, well, why do we need a new data set for vision and language navigation? So there's a couple of reasons, a couple of things that motivated this work. Firstly, the majority of work in this language-guided navigation or vision and language navigation space is English-centric. So we wanted to create a data set that was multilingual. In this case, it includes English, Hindi, and Telugu. Secondly, hopefully this has been well motivated by now, but we wanted to increase the scale. And so the RXR data set is around 10 times the size of similar data sets. It includes over 100,000 instructions and something in the order of 10 million words. It also contains fewer path biases in terms of the way the paths are constructed, and the viewpoint coverage is more uniform compared to previous data sets such as room to room. Fourthly, we include a follower demonstration of every single path, which is a nice way of ensuring the quality of the data, but it also provides additional signal in terms of a human blow by blow description of exactly how a person follows that path. And finally, hopefully this was clear from showing you the annotation interface, but we capture this spatio-temporal grounding. So by recording voice and transcribing it to text, rather than using text input, which was used by the previous data sets, we're able to align every word in the instruction with what the annotator was looking at as they recorded that instruction. In order for that to work, there's a neat idea that we borrowed from previous work on the localized narratives data set. And so basically, in order to get the alignment between each word in the instruction and the pose trace, which captures what the annotators were looking at, we first perform a automatic transcription of the voice recording, and then we compare that with the manual transcription created by the annotator. And by aligning the two, we're able to propagate the timestamps from the automatic transcription into the manual transcription. So ultimately, the output of this setup is a manual transcription that's timestamped to match the pose trace, indicating what the annotators were looking at. And by the way, our complete annotation toolkit called Pangea has been open sourced, which performs all of this work. So to put that in perspective, here's another view of that same annotation, which shows the path taken by the annotator in the context of a 3D mesh of the environment, and the color coding between the arrows and the light cast by the annotator's camera view aligns to the words in the text instruction shown on the right-hand side. So this is exactly what the spatio-temporal grounding that we've collected can look like. We can also look at this in terms of image space rather than a 3D mesh. So it's very interesting to see when we follow the movements made by this annotator and look at which pixels at each point in time of the 360-degree image, which pixels they actually looked at. You can see a nice alignment here between, say, in the second image, the wall painting, which is seen in the image and then mentioned in the instruction, and so on. And so this is a really nice alignment between image and text, which we hope will be useful for training in various ways. And you can see a very similar alignment. So this is for the follower task, where a separate annotator is charged with following this navigation instruction. And again, we see a very similar alignment between the vision and the text. Just to briefly survey some of the interesting linguistic phenomena in the RXR instructions, in this case, in comparison with the R2R dataset, because the instructions and paths are generally longer, we see quite a lot of co-referencing. There's also a lot of sequencing in terms of an ordering that's provided to the instructions. We see a lot of mentions of allocentric relations, such as a window with a black folding table under that. So the position of the table is described with respect to the window as opposed to the observer. And there's this interesting and fairly new phenomenon for these data sets, which is we call state verification, where the annotators will frequently describe nothing more than what you should see at this point, and that can be used to verify that the instruction has been followed correctly so far. So based on this data set, we've released a number of interesting challenges. The RXR challenge is a multilingual vision and language navigation challenge using the RXR data in Matterport 3D environments. And in this challenge, the agents navigate through a graph-based environment, which is the kind of typical approach for these styles of data sets. We've seen some interesting advances on the leaderboard, and this is open for ongoing submissions to try to close the gap to human performance. Now, as well as the RXR challenge, we've recently also released the RXR Habitat Challenge. And so this uses the same RXR data and the same environments, but in this case, it combines with the Habitat Simulator, which allows for a low-level continuous motion in the environments rather than using graph-based environments. As you can see from this example here, this is a very, very difficult challenge because it involves not only multilingual language understanding and grounding, but also low-level control of the agent. To help get things started, we do provide starter code in PyTorch, and there's a leaderboard as well, which is available on an ongoing basis. So thank you very much. I hope the talk's been enjoyable, and certainly hope that other people have found this research program exciting. And I would like to finally acknowledge many of my awesome collaborators who've worked on the 3 projects that I've outlined so far. Thanks very much.